Series of lessons on heat transfer. This is Rama Krishna from KL University. We are in lesson 5 now. Till now we have seen what is conduction and convection and radiation, and we have developed the three-dimensional conduction heat equation in Cartesian, cylindrical and spherical coordinate systems. But most of the classroom problems, as I told you, are based on one-dimensional only. We can solve the problems in a classroom in a stipulated time by taking an assumption one-dimensional. So we will concentrate now onwards on one-dimensional heat transfer, particularly by conduction and through different geometries. And finally, after completion of the conduction, we go in depth into the convection and radiation. So now going in deep into the one-dimensional conduction, we have already seen through a slab the rate of heat transfer by means of conduction is Q equal to K into the area normal to the direction of heat transfer into temperature difference across the faces T1 minus T2 divided by L. But when it comes to cylinder and sphere, a little bit variation is there, slightly difficult. So we'll see in this session how to calculate one-dimensional steady state heat conduction without internal heat generation through a hollow cylinder and sphere. At the end of the session, the student is able to understand how to calculate heat transfer through a cylinder and how to calculate heat transfer by means of conduction through a sphere, and how to account for variable cross-sectional areas in conduction, and what is logarithmic mean area and what is geometric mean area. Conduction heat transfer through a hollow cylinder and sphere. As I specified earlier, most of the engineering devices involves the flow of fluids through pipes or objects in cylindrical shape. So therefore, it is assumed that the heat flow through the pipes is in radial direction only, and there is no heat transfer along the axis. That is, at any radius along the axis, the temperature is uniform. So we consider only heat travel in radial direction. Just follow this arrow. I will try to explain. Suppose the temperature at this point on the outer black circle is say 100 degrees centigrade. Carefully follow. At this point is say 100. The temperature here also 100. The temperature here also 100 degrees. The temperature here also 100 degrees. That means I am not considering the variation of temperature in theta direction. Follow carefully. I am not considering the variation of temperature in theta direction because all along this outer circle surface temperature is 100 degrees only. Next, what is the temperature here? 100 degrees centigrade. Temperature here is also 100. Here also 100. At this point also say 100 degrees centigrade. That means all along the length of the cylinder, the temperature on the outer surface is the same, which means I am not considering the variation of temperature in Z direction. So only thing is the temperature at this point, outer radius is 100, maybe inside here it is 30. So there is a variation of temperature in radial direction. So the temperature variation is only in one direction. It becomes a one-dimensional conduction heat transfer problem through a cylinder. I am neglecting the variation of temperature in theta direction. I am neglecting the temperature variation in z direction. So now the problem simplifies to a one-dimensional conduction heat transfer in radial direction. See, like this. Imagine the inner surface is at high temperature, outer surface is at low temperature. Now the heat flows in the radial direction. While heat is flowing, you can imagine as it flows by means of conduction, the temperature gradually drops, and the rate of heat transfer by means of conduction through the cylinder wall can be determined again by using the Fourier law of conduction, which says Q is equal to minus Ka dt by dx. Here dx is thickness in the direction of heat flow, maybe R0 minus Ri, and dt, temperature difference, inner surface and outer surface, no issue. K, thermal conductivity of the cylinder material, it is also no problem. But the area is the area which we have to consider normal to the direction of heat flow. So if you consider normal to the direction of heat flow, when heat is flowing from, see, this inner white circle to the outer circle, the area available for heat transfer normal to the direction here is the circumference of this white circle 2 pi Ri into length. Whereas at the outer periphery, perpendicular to the direction of heat flow, at the outer periphery the area is 2 pi R0 into L. So the area changes. How to account for that change in area? This is the important consideration in cylinder and sphere. While heat is flowing radially outwards, maybe from inner surface to outer surface or outer surface to inner surface, as the heat proceeds, the area normal to the direction of heat flow gradually changes. Under such circumstances, what we will do is, we will consider an elemental strip at a radius r having thickness dr. The thickness dr is very, very small, such that r plus dr is approximately equal to r. The heat passing by means of conduction from inner surface to outer surface is say Q. Then according to energy balance, the heat passing through the elemental strip is also Q. It enters as Q and leaves as Q. So by conduction, the heat passing through this elemental strip is also Q at a radius r, where r varies from Ri to Ro, and the thickness of this elemental strip is dr. So for this elemental strip, the inner area normal to the direction of heat flow is 2 pi RL, outer area strictly speaking 2 pi R plus dr into L, but R plus dr is approximately equal to R, hence we consider the area of cross section when heat is flowing through this, normal area through this is same. Now as per the Fourier law of conduction, Q equal to minus Ka dt by dx, where the area at this inner element is 2 pi r into L. L is the length of the cylinder, and in place of dx you have the thickness dr. And now Q equal to minus K, area is 2 pi RL into dt by dr. Bring this dr to the left hand side. Q dr by 2 pi K RL equal to minus dt. R varies from inside radius to outside radius. Temperature varies from Ti to T0. So by integration you will get Q by 2 pi KL. Integration is upper limit and lower limit in the same order. Log R0 by Ri equal to minus dt integration is T, upper limit and lower limit substitution, minus T0 minus Ti. Therefore Q equal to minus 2 pi KL T0 minus Ti by logarithm of R0 by Ri. Or we can write Q, conduction heat transfer through a hollow cylinder having outer radius R0, inner radius Ri is given by 2 pi KL Ti minus To by logarithm of R0 by Ri. Very important, remember it. The same equation now can be written like this. You multiply both numerator and denominator with R0 minus Ri by R0 minus Ri. And in the place of log R0 by Ri, again you multiply R0 and Ri, both numerator and denominator, with 2 pi L, 2 pi L. Now K as it is, 2 pi L into R0 is A0, 2 pi L into Ri is Ai. So 2 pi L R0 minus Ri becomes A0 minus Ai, logarithm of 2 pi R0 L A0, 2 pi Ri L Ai, Ti minus T0 by R0 minus Ri. This A0 minus Ai by logarithm of A0 by Ai is known as logarithmic mean area. So hence we can write Q is equal to K into logarithmic mean area into delta T by delta R. General conduction equation is Q equal to Ka dt by dx. So in the place of A you have logarithmic mean area, which is A0 minus Ai by logarithm of A0 by Ai. Hence we can conclude that the area of cross section, rather the equivalent area of cross section for a cylinder is logarithmic mean area. I will repeat, the equivalent area of cross section for conduction heat transfer through a cylinder is logarithmic mean area. Q is equal to Ka logarithmic delta T by delta R. Logarithmic mean means A0 minus Ai by log A0 by Ai. The equivalent heat transfer area in a hollow cylinder is equal to the logarithmic mean heat transfer area of inside and outside areas. Now let us see the conduction heat transfer through a hollow cylinder, hollow sphere. The same equation, Q equal to minus Ka dt by dr. dr is the elemental thickness at a radius r. R varies from Ri to R0. A is the area normal to the direction of heat flow when heat is flowing from inner surface to outer surface in one dimensional R direction only. We neglect the temperature variations in theta direction and phi direction, hence we consider only heat flow in radial direction. The surface area is nothing but the area of cross section for the heat transfer to flow. So A is equal to 4 pi R square. So Q is equal to minus K, in the place of A 4 pi R square dt by dr. This is Q by R square into dr equal to minus 4 pi k dt. dr by r square, integration is minus 1 by r, limits r0 r1, minus 4 pi k, dt integration is t, so it becomes t0 minus ti. So it is minus q, upper limit and lower limit substitution, 1 by r0 minus 1 by ri is equal to minus 4 pi k t0 minus ti. So it simplifies to q is equal to minus 4 pi k r0 ri into t0 minus ti by r0 minus ri, which can also be written as minus r0 ri t0 minus ti. This 4 pi k comes into the denominator as 1 by 4 pi k, and r0 ri, when it comes to the denominator here, r0 minus ri by r0 ri, it becomes 1 by ri minus 1 by r0. Minus sign goes inside, t0 minus ti becomes ti minus t0, higher temperature, lower temperature. So this q can be written as k into t0 minus ti by, look here, k t0 minus ti by r0 minus ri. Then the left out thing is 4 pi r0 ri. So what I will do is take 4 pi r0 ri as it is left out, multiply with another 4 pi r0 ri and put it under root. So equation remains same. Now consider this 4 pi r0 into 1 r0 here becomes 4 pi r0 square a0, and ri is left here, and 4 pi ri. 4 pi ri square is ai, and hence q becomes k root of a0 ai t0 minus ti by r0 minus ri. This square root of a0 ai is known as geometric mean area. Hence, conduction heat transfer through a sphere is minus k into geometric mean area of inner and outer surfaces into delta T by delta R. The equivalent area for conduction through sphere is geometric mean of inlet and outlet areas. In case of cylinder is logarithmic mean of inlet and outlet areas. In case of slab, the area inside and area outside is same. It is A only. So I can say the equivalent area for conduction through a slab is arithmetic mean of inside and outside areas, because A plus A by 2 is A again. So we can conclude that in case of slab it is arithmetic mean, in case of cylinder it is logarithmic mean, and in case of a sphere it is geometric mean. The students are advised to remember these three equations carefully. Now let us have a look at few problems related to the application of heat transfer through a hollow cylinder and sphere. Unlike in the first exercise, I am not going to write all the data and I am not going to specify the assumptions here, and all those things are essential because of paucity of time. I will just give you how to solve these type of problems in a quick way. Imagine a hollow steel cylinder, inner diameter 25 mm, that is radius is 12.5 mm, outer diameter 32 mm, that radius is 16 mm. Thermal conductivity of the cylinder is 30 watts per meter Kelvin, maintained at 60 degrees and 50 degrees, and the length of the cylinder perpendicular to the paper is 0.75 meters. Determine the rate of heat transfer. It's clearly a problem on hollow cylinder. The equation is 2 pi KL Ti minus T0 by logarithm of R0 by Ri. So K is 30, length is 0.75, 60 minus 50, logarithm of R0 by Ri, you will get the answer. Don't worry about this resistance. next session we will take up, and then we will understand what is this figure drawn here. Next, another one. A hollow spherical container made up of styrofoam, thermal conductivity, I'm sorry, here it is shown 0.78, but actually 0.033, with outer dia 20 centimeter and inner dia 19 centimeter, is filled with ice at 0 degrees centigrade here. If the outer surface is at 5 degrees, determine the approximate rate of heat absorbed by ice and the rate at which the ice melts in the container. Take latent heat of fusion of ice is 333.7 kilojoules per kg. Anyhow, so we are interested in determining the conduction heat transfer through the hollow cylinder. It is given by the formula Ti minus T naught by 1 by 4 pi k into 1 by R naught minus 1 by Ri. This one. So 1 by 4 pi k, 5 minus 0, 1 by R naught minus 1 by Ri will give you 3.94 watts. This is the rate of heat transfer. You know the latent heat is 333.7 kilojoules per kg. Divide this 3.94 with this, you will get, this is in watts and whereas this is in kilojoules. Convert this into joules per kg and divide, you will get how much ice is melting in the container per second. So again, the listeners are advised to give a reading of these textbooks, preferably before going to the next session. Thank you very much. Thank you, one and all.